Welcome back, everyone. If you're a focused learner looking to totally master the intricacies of programming, you are in the exact right place. Today, we're jumping into our explainer of Lecture 37 by Skip Uni, and we are tackling a seriously important topic, something you absolutely need to know for technical interviews, competitive exams, or really just your standard university tests. We're talking about the dreaded memory leak in C++. So to get you fully prepped, we're going to be looking closely at memory management in C++. We'll dive deep into exactly how memory leaks happen, we'll explore the hidden risks of dynamic memory allocation, and of course, we'll master the proper use of new and delete in C++. Let's jump right in.
So here's a question for you. Is your C++ code secretly leaking memory right now? I mean, it's a pretty scary thought, right? Failing to grasp this, admittedly kind of abstract concept, isn't just a minor technical oops moment, it's exactly the kind of subtle bug that can outright ruin your performance in high-pressure technical interviews, totally tank your scores in competitive exams, and worst of all, in the real world, it can cause massive, long-running systems to slowly grind to a halt and just crash. It is, quite literally, a silent killer of programs.
Okay, let's dive into this. Here's our roadmap for today. Number 1. What is a memory leak? Number 2, stack versus heap memory. Number 3, the anatomy of a leak. And finally, number 4, preventing leaks manually. Starting with Section 1, what is a memory leak? At its absolute core, a memory leak is all about wasted memory slots in your system. It's about occupying space that you don't actually need anymore, but you're refusing to give it back. To really understand this, we've got to look at dynamic memory allocation. This is when you request memory at runtime specifically by using the new keyword rather than knowing the exact amount beforehand when the program compiles. Now, static memory allocation, that is entirely safe. The system just automatically knows exactly how much memory is used and frees it up for you, no questions asked. But the second you step into dynamic allocation, you are taking the training wheels off. You introduce the very real risk of human error. And that human error leads to this precise situation. Memory that's allocated but never released. A memory leak is really just this simple, devastating mistake. Basically, your program successfully asks the system for memory. The system graciously provides a slot, but your code entirely fails to release or deallocate that slot after it's done using it. So the memory just sits there, completely trapped.
Moving on to Section 2, stack versus heap memory.
To really visualize how memory gets trapped like this, we need to introduce the two completely distinct environments where our code actually operates. Think of stack memory as a temporary whiteboard. It is automatically managed by the system, it's highly limited in space, and it holds your local variables. When you're done, the system just wipes the whiteboard clean automatically. Done. On the other side, we have heap memory. I want you to think of the heap as this vast, permanent warehouse. It has massive space for dynamic allocation, but, and this is a huge but, it is entirely manually managed. When you put an item in this warehouse, it stays there permanently until you explicitly walk in and remove it.
Section 3. Anatomy of a leak. Now, what's really interesting about this slide is how we can break it down step by step.
Let's follow the journey of a single variable to see exactly how a memory leak is born. We'll walk through these steps as our program runs. Step 1, our main function starts, and the system creates a stack frame, like an activation record, right there on our temporary whiteboard. Step 2, main calls another function, let's say function 2, creating a second frame on the stack. Now, inside function 2, we have a local variable n, which takes an input size from the user. Let's say they type in 100. Step 3, and here is where the magic happens. Using the new keyword, the program dynamically allocates an array of size 100. Because this is dynamic, this array is built out in the vast warehouse, the heap memory. But to interact with that distant array, we have to create a pointer, PTR, back in our stack frame for function 2. So the pointer on the stack strictly points to the array sitting way out there in the heap. But here is the crucial point. What happens next? Step 4 is the climax of our story. As the quote goes, the pointer is dead, but the memory lives on. You see, when function 2 finishes its job, control flows back to main, and the system does exactly what it's supposed to do. It automatically wipes that whiteboard clean. It auto-deletes the function 2 stack frame, which instantly destroys the variable n and our pointer. But remember what we said earlier? The heap doesn't auto-delete. That dynamic array of 100 elements is still sitting out there in the warehouse. Because the pointer is gone, that array is now completely orphaned. It is taking up space, but we have absolutely no way to access it or clear it out. Ladies and gentlemen, you just witnessed a memory leak.
Finally, Section 4, Preventing Leaks Manually. Okay, now that we've seen the disaster unfold, how do we actually save our programs from this black hole of wasted memory space? Well, the programmer must take manual responsibility. Because the heap is a manual environment, our vast warehouse, the system is never, ever going to clean it up for you. It assumes you put the data there for a reason, and that you will take it out when you are done. This makes it your ultimate duty, as the coder, to step in and intervene.
So let's look at how you actually intervene. Here are your 2 syntax lifesavers. If you allocated a single standard variable, you release it by simply typing delete, followed by your pointer. Delete PTR. However, if you dynamically allocated an array, you have to include square brackets. So you write delete, open and close square brackets, PTR. And honestly, the most critical part of this whole thing? The timing. You must execute this command before the function ends. By running this delete command, you successfully deallocate and clear out the heap memory while your pointer still exists to actually guide you there. Once the memory is freed, the function can safely end, the pointer is wiped from the stack, and your system stays perfectly clean.
So, before you compile your next project, ask yourself, have you checked your dynamic arrays for orphaned memory today? Seriously, because if you haven't, your program might already be dying a slow, silent death. Understanding this really simple relationship between the temporary stack and the permanent heap is the absolute foundation of good code hygiene in C++. Without it, you are silently draining your system's resources every single time your program runs. So take this knowledge, go open up your latest C++ projects, and make absolutely sure every new has a matching delete. Thank you so much for joining me on this explainer, and happy coding.